So here we have an interesting conservation of energy problem. We're told that a bullet is fired into a wooden block that's hanging vertically. After the collision, the bullet completely implants itself into the block, and the block swings up to some angle that we can measure. Alright, before it momentarily comes to rest. And the question is, how fast was the bullet moving before it hit the block? Right, so this problem is actually two processes in one description, right? One problem here. We have the bullet hitting the block, and then the whole system swinging up. So the bullet hitting the block, this is an inelastic collision. In fact, it's a perfectly inelastic collision, right? And the before is drawn already, but the after for the collision is left out. Alright, so let's draw that quickly. This is the bullet with some V initial and the block just hanging. So this is our before. And afterward, the bullet implants itself into the block, and the whole system has some velocity v final. Alright, so this is just before it starts to swing up. So here's the after. Okay, so there's our inelastic collision, and then just after the collision, the whole system swings up to some final position. That is a conservation of energy problem, right? So we'll write that here. Right? I mean, clearly, energy is not conserved in this inelastic collision, right? But once the collision has taken place, the block swinging up does conserve energy because the only force acting here is gravity, and we can include that as potential. So the after for the collision becomes the before for the conservation of energy problem. Right? In fact, I'll draw an arrow to indicate that. This becomes this before. So we'll draw it again. And I'm going to keep this as a V final, even though this is our new before. This V final is equal to that V final. Alright, and then this thing swings up to some angle. It's drawn better up here, the image is up there. And it's at rest for a second. So there's our after. So again, we're solving for V initial. That's what we're trying to find. We know how high this swings, right? It swings up to 55 degrees as labeled on this diagram. So maybe we can use conservation of energy to figure out V final, right? This V final, or the V just before it starts to swing upward, and then we can use momentum to find V initial. Okay, so let's look at the conservation of energy bit first. Looks like we should say energy initial equals energy final. The initial energy is all kinetic, right? If we call this height to be 0. So the initial energy is all kinetic, and the final energy is all potential, U final. So we can write down those terms. This is 1/2 m, and that's mass of the block and the bullet. So maybe I'll make it a capital M. 1/2 m V final squared equals mgh, where h is the height that this block swings to. So we should figure that out. So if we trace this over a little bit, and then trace this back, I didn't trace it quite straight. This little distance here, that's h. Okay, so one way to figure this out is to label this Y initial is 30 centimeters, right? And Y final is this side of this triangle. Now this string is still 30 centimeters long, and theta was given as 55 degrees, so it looks like Y final is 30 centimeters times a sine of 55 degrees. And if you do that, I think you get 24.57 centimeters. So then H is the difference of those. It's 30 minus 24.57, and what you get is 5.43 centimeters. So we can plug that number down in our conservation of kinetic energy. So when we fill out this equation, we could fill out the masses of these things, but you notice that it cancels out. So the masses go away, which is convenient, and we can solve for V final. V final looks like it's the square root of 2GH. I can plug in numbers for that. It's the square root of 2 times 9.8 meters per second squared times this 5 centimeters, which is 0.0543 meters, so that I get a number that is in meters per second. And it turns out to be 1.03 meters per second. So now that is the V final that should go into our inelastic collision. So again, energy is not conserved in this inelastic collision, but because there are no external forces, momentum is conserved. Okay, so this is one of those kind of dovetail problems where it's two kinds of problems kind of interconnected. So conservation of momentum says that the total initial momentum equals the total final momentum. Now the initial momentum is all carried by this bullet, right? The block's not moving, so it must be m bullet times v initial. And the final momentum is this whole system moving at v final. So I'm going to combine the masses. It's mass of the bullet plus mass of the block times v final. It's a fairly straightforward equation. So now we're just solving for v initial. So I'm going to solve for v initial and plug in the numbers all in one step. Looks like v initial should be, it's a 5.5 gram bullet, so it's 5.5 times 10 to the minus 3 kilograms plus a 1.2 kilogram block times v final is 1.03 meters per second, all divided by the mass of the bullet, 5.5 times 10 to the minus 3 kilograms. And if you do that math, you end up with 226 meters per second. And if you round to 2 sig figs, you get 230 meters per second. So the final step should always be, is this a reasonable answer? And yeah, this seems reasonable for a 5 gram bullet. If you've looked at the speeds of bullets before, for a 5 gram bullet, this is pretty reasonable.